Okay, so here's the homework, chapter 16. We're skipping chapter 15. We will come back to it after we do, I think, the next two chapters. We got a lot to cover tonight, so we'll see how far we get. We're going to talk about carboxylic acids and esters. What is a carboxylic acid and what is an ester? Okay. First of all, let me just write a little note on here. And there are PowerPoints and PDF files for you guys to work with. So if you want to know a couple of good programs for, if you have like an iPad or a tablet, if you get like Notability or GoodNotes, those work really well with just writing on the slides. And you can zoom in as big as you want. The reason I use GoodNotes is because your handwriting is searchable. So you make a PDF of the file, you can search through the text of the slides, and then when you write on it, it converts your handwriting somehow into text. And then you search for on an exam, or you search exam question, it will find that in your slides. Yeah, it's really cool. Plus, if you just want to make like fluffy clouds and trees, they've got all kinds of other pen things you can do. So carboxylic acid. That's that guy that looks like this. I'm just going to write it on here. That's a carboxylic acid. We write him lots of different ways, or her, sorry. It doesn't really matter. COOH, that's another way. And then sometimes you'll see it, and I hate this one, CO2H. But those are all ways of writing carboxylic acids. What is it? It's a carbonyl group, right, with an alcohol on it, which makes it acidic. So what do acids do? They lower the pH by giving up protons, the hydrogen ions. Okay, so that's what those guys do. And esters are very closely related to carboxylic acids. Here's a very simple ester. And you notice so far, what have I done? I've done exactly what I would have done for a carboxylic acid, except now I stick another carbon over here. So that would be an example of an ester. Esters are really cool. The small ones smell like fruit. They actually really like pretty smelling, like bananas and blackberries and strawberries and pineapple. Those are all esters. They all smell yummy. What's that? Yeah, last week we made banana oil, but we could have made pineapple, we could have made blackberry, we could have made pear, we could have done all kinds of stuff. Mostly we don't do that just because, you have lots and lots of chemicals that you have to store and stuff. Okay, anyways. So, real quickly, we're going to do a couple of quick review items. Writing equations for reactions of acids and bases. So let's say I have an acid, like, and I'm going to use acetic acid. Do you guys remember what acetic acid is found in? No, that's citric acid. But we'll talk about citric acid. Oops, sorry, got a little carried away. It's vinegar. So you find acetic acid in vinegar. You find it in really bad wine. In fact, I bought a bottle the other day, and I've had it before, and it was really good, and this one's just horrible. And I'm like, I can't drink this thing. So it's all down the drain. That's okay. I don't miss it that much. So there's my acid. If I'm going to do a base with it, who has a favorite base? What's your favorite base? You don't have a favorite base? Sodium hydroxide? Yeah. Okay. Now, when you have an acid-base reaction, it's called a neutralization. And the products are always what we call a salt and water. So we know water is one of the products, okay? In this case, it's going to be H2O. Now, if water is one of the products, that's actually this H and this OH, right? Then what I end up with, I ran out of space, is, I like this color better, CH3, C double bond O, O minus. You get a negative sign there, and Na plus. When you did this in Chem 3A, you probably didn't write acetic acid like as a Lewis structure. It was probably just CH3COOH. So if that part's confusing, you probably wrote it like this. Plus NaOH. Now, how did I get that? Right? This is the anion, right, on the left here. And you do a double replacement. Now, in organic, and if it helps you for writing these, in organic chemistry on carboxylic acids, you know how the hydrogen's on the end, right? If it helps you to do these correctly, just get rid of that and put it on the front. And that's the way you learned it in like general chemistry. The hydrogen's always in the front. It's an acid. It's okay to just move it from the end to the front for this kind of stuff. And then this is the double replacement reaction, if you remember that. So this part goes with that part, and this part goes with that. And so that's how I got those products. You might have to do a little bit of reviewing on that. You know that water's one of the products, and then you always get this anion from the acid, right? And because it has a negative charge and sodium has a positive charge, these things go together. All right, questions? We can practice more in lab if you want to do more in lab. We'll just write a bunch on the board. We'll just do them, okay? Alkanes, I'm not going to review that. We've been over that lots of times. So. All right, so carboxylic acid group has this carbonyl functional group, and it has a hydroxy functional group. What we're going to learn is how to name them. What do you think the first thing you do when you name one of these is? Parent chain. Yeah, it's the first thing you do in all of these things. So I have a carboxylic acid. What you need to do when you name it is you first need to find what the parent chain is, and then you figure out how to name the parent. And then once you do that, what do? Parent, name the parent, substituents, and then put it all together. It's the same thing that we've done before. So, give you some quick examples. The way that you name these compounds, and I actually took the slides that the textbooks put together. I think I shoved them all the way at the end because they have a lot of words on the slides, and I try to simplify it for you guys. The way that you name the carboxylic acid, this one, for example, it has one carbon, right? So one carbon is methane. You get rid of the E, and you put oic acid on it. So this is methanoic acid. And all I did was take the E from the methane and put OIC. Get it? OIC. Never mind. It's not funny. I try to make it funny. Methanoic acid. Ethane, right? 2-carbon carboxylic acid, named after ethane, becomes ethane, and then get rid of the E and put OIC acid on there. And that's how you name the parent chain for all carboxylic acids. Right? How do you do alcohols? You get rid of the E, add OL. How do you name aldehydes? You get rid of the E and put AL. Ketones, get rid of the E, put ONE. Right? It's kind of the same all the time. So that's how you name the parent chain. Carboxylic acids, though, you have to be careful now, have the highest priority of any of the functional groups that we've encountered, and I think they're the highest priority in the entire list. So what that means is, the implications of that is if you have a ketone in there, okay, it becomes an oxo. And if you have an alcohol on the chain, that becomes a hydroxy. So those are things that you have to be aware of. Now that the carboxylic acid is the highest priority, and it is also always at the end, right? So it doesn't need to have a number. You would say oxo for carbonyl groups instead of ketone or aldehyde names. And you would say hydroxy for alcohols. And we talked about aldehydes, we use formal as well. And those are on a previous lecture set. All right. So let's name these. We named the first one. The carbon of the carboxylic acid is always number 1. Okay. So just to start us off, I put a 1. The one on the left is methanoic acid, so we named that one already. What's the parent for the middle compound? Propane. It's got 3 carbons in it. The parent includes the carbon in the carboxylic acid. So this becomes propan, because it's propane, right? I'll get rid of the E and OIC. I'm already tired of saying it. Propanoic acid. Now, we're going to number from there, so that's 2 and 3. So what do I have on there? I have a methyl group, so it's 2-methyl, right? Propanoic acid, and this just goes in front like that. Next one. What's the parent? Butane, right? So butanoic acid. And again, you don't have to say where the carboxylic acid is because it's always at the end. Now, on 3, what is that? 3-hydroxy. Okay, so you find the parent chain, number the carboxylic acid from the carboxylic acid end, you number the substituents, and then when you put the name together, these only had 1, you do them in alphabetical order, and then I'm just warning you here, use oxo, hydroxy, formal as appropriate, because those are no longer the parents of this molecule.
How do we know how to use hydroxy or hydroxyl?
Oh, hydroxy is just what it is. Yeah.
So if it's attached.
A hydroxyl group is like when you're just generally describing what it is, but as a substituent you say hydroxy.
Oh, okay. So
Wait,
for
is
the
that right?
naming, we
Hydroxy?
do hydroxy.
Yeah. Do I have that right? I think I have that right. Yeah. Yeah, for the naming you do that. Oh, one other thing. These sometimes have common names, okay? And remember, I've talked about these before. I actually think I have it on a separate slide, but I'm going to go ahead and do it here again. 1 carbon is form. So if you're naming this compound number 1 using its common name, you use that prefix system for 1, 2, 3, 4, 5. That's form, acet, right? Propion, yeah, that's a weird one. And then butyr, right? So this becomes 1 carbon becomes formic acid. 2, 3 carbons would be propionic acid. Okay, it's got too many syllables. And then 4 would be what?
There's no R. It's propene.
Oh, okay. Yeah, there we go. Thank you. Oops. I didn't mean to do that. I lost my edit. Well, that stinks. So yeah, propionic acid. Propionic. I'll just rewrite it. That would be for 3. And 4 would be butyric acid. And the only reason, it's on the bottom. Somebody messed with the screen again. Only reason I mention these is because they are common names. Did I get it all on that time? I did. Good. Okay. Oh, yeah. The whole top of the slide is missing, like the title of the slide and everything. Okay. Well. Another couple of common, well, at least one common name that is part of the systematic nomenclature is benzoic acid. So benzoic acid is a benzene ring, right, with the carboxylic attached directly to the carboxylic acid. So we call that benzoic acid. What is PABA? Anybody know? PABA. Sunscreen. That's what you see in sunscreen. Benzoic acid is actually used as a preservative in food that you probably don't want in your food. Because with citric acid, if it gets heated up, produces benzene, and then benzene's bad for you. But it's in a lot of stuff. It's kind of hard to avoid. Let's see, dichlorobenzo. Yeah, actually, this is closely related to the stuff that's in toilet bowls, but it's not the stuff in toilet bowls. So, and this is if you'll notice, when this is the parent now, so that's the parent, the number 1 is always placed where the carboxylic acid is attached. And so then you count around on these rings. This is 1, 2, 3, 4. So that one is 4-amino. That's what we call an amine as a substituent for aminobenzoic acid. But we also learned before that you can do ortho, what's the other one? Meta and para. If it's on the 2, this is the ortho position. If it's on the 3, it's the meta position. If it's on the 4, that's the para position. Okay, that's kind of a reminder. This is 3,4-dichlorobenzene, just based. Yeah, it used to be a lot of sunscreens had PABA in it, or PABA, or p-aminobenzoic acid. Yeah. I'm trying to think. I think we used that in acetaminophen synthesis. I'm trying to remember now. I'll have to look that up. That would be an interesting thing to talk about. All right. A couple of other things to recognize in common names, unfortunately, is sometimes they don't use the numbers. And they use alpha, beta, and gamma. And so on a carboxylic acid, if you draw a line here, you'll notice the first carbon, right, is the alpha carbon. The second carbon away from the carboxylic acid is the beta, and the third one is the gamma. So one way to name something like this as a common name would be to call it butyric acid, okay? So if I was going to do that and just go all out on the common name, you would write butyric acid. And then this methyl group is in the beta position, so it would be beta methyl butyric acid. So you would literally write a beta methyl. I'm not a big fan of this kind of nomenclature, but it does come in a couple of places, like in biochemistry, where you need to know what is alpha, what is beta, what is gamma. And so it's helpful in those compounds to have an understanding of where they're at. As far as nomenclature goes, at this point, I'm probably not going to ask you to give me alpha, beta, gamma, but I'd rather you just do 1, 2, and 3, and 4, right? But then when it comes to, when we talk about steroids and things like that, you'll have to know some alpha, beta, and gamma then.
So that nomenclature, it doesn't start from the first carbon?
Yeah, it doesn't start from the first. It's the first one next to the functional group.
Only on the common name.
But only in the common name. So if you're going to name this like a mixture of common name and systematic name, you would probably say 3-methyl butyric acid. That's going to be something you'll see. Okay, that's not an uncommon thing to see.
How did it become butyric?
Oh, because it has 4 carbons,
And that's the common name.
and that's the common name, yeah.
So it would be just bu, the way the other one, O-I-N, or the other?
Yeah, it's like, yeah, they're all up here actually, right here. Form, acet, propion, butyr. Then there's like, I also said there's like valor. So like 5 carbons would be valeric acid, 6 carbons would be caproic acid. That's the one that smelled like goat. Remember I told you it smells like goat? Yeah. Or I might have mentioned it smells like goat. Okay, just a couple of side things. All right, methanoic is also known as formic acid. That's what you get, and when you get stung by those red ants, they bite you and it stings. That's formic acid. And then ethanoic acid is what we find in vinegar, and all these are different. Like this is like regular vinegar, and then wine vinegars and stuff like that. Basically, those are all that sour flavor that you get is acids. Okay, citric acid is Sour Patch Kids. It's the sour of Sour Patch Kids. Okay, so that's where we get our sour flavors from. They're actually pretty good preservatives too, because they're so, when you put acids in things, they become more acidic, and it inhibits the growth of like bacteria and mold and stuff like that. This is the rules from the book. I'm going to skip over these, but I thought we're going to go ahead and do this one. What is the IUPAC and common name? So IUPAC is easy. How many carbons? 5. So what is that? Pentane, right? So we're going to go just through the whole thing. I identified the parent as pentane. That becomes pentanoic acid. And then we number it from the carboxylic acid in just to make sure we don't miss the numbers. And double check that we got 5. Yeah, we got 5 here. And I have a hydroxy, an OH group, right? So it's going to be 3 hydroxy pentanoic acid. So common names, it's a 5 carbon, and what I'd mentioned before, that's valeric acid. V, remember the V looks like a Roman numeral 5. So this is valeric acid. And we'll go all out. Let's just go do the alpha beta thing. Which carbon is the alpha carbon?
Oh, CH2, like we don't know.
Huh?
CH2.
The CH2, this carbon?
Yeah.
That's the alpha, right? And this is the beta. This would be gamma and delta. So this is alpha. So it's the beta is this one, okay? So remember, when you do this alpha beta thing, always start from this position next to the carboxylic acid. Alpha, beta, so this is beta hydroxy. And then you put it right there. The pen is skipping a little bit. Okay, we'll do another practice. What is that? Parent. It's got a benzene on it, right? So there's a benzene, and then there's the carboxylic acid, so this is benzoic acid. That's the parent. And like I said, if you don't, that's one of those things you memorize. Oh, look, I lost the tip to my pen. Goodness gracious. That's a miracle I found it. I actually just brought some extra ones in too. I'd have to raid my wife's office to find them though. I stuck it in her office because I wouldn't lose it there. So, yeah, I think this will work. So this is benzoic acid. And then when you number benzoic acid, you start from the carboxylic acid, and then you go in the direction that gives you the lowest possible number for this first substituent. So you're going to go in this direction. Now, you have choices about naming this that both are acceptable, so I don't care how you go on this, but you can say 3-bromo, benzoic acid, and then the other one is to remember this is 2 is ortho, meta, and para. So you could say M-bromo, benzoic acid.
Are we ever gonna have
It just depends. Like, so I might give you a name and ask you to draw it, for example, right? Then you would have to know O, M, and P, because I might give you one or the other. If I ever ask you to name something and it's not multiple choice, I don't care how you do it, as long as it's correct, okay? So, yeah, that's about the only way to really put that. Now, O, M, and P, by the way, only work when there's 2 things on the ring. If there's 3 things, you don't use 2 letters to describe them. You just, it's for 2 things, okay? Okay. Something else I wanted to say about that, but I don't remember what it is.
Isn't that a common name when we do the N?
No, that's part of the systematic name, I think, yeah.
So it shows common name.
Yeah, but it uses that, but you see it all the time, so I would just treat it as a systematic name.
I have a question.
All right.
So no matter
Bodiless
how many
voice.
bonds it is, it doesn't matter. It's always going to be the OIC at the end. Like
Yeah,
even if-
yeah. As long as it's a carboxylic acid, then you put OIC at the end. Okay, so now we're going to do 4-chlorohexanoic acid. So we're going to start, draw the parent chain, and then attach a carboxylic acid to the, as part of the parent chain. So hex is 6, right? So we're going to do 1, 2, 3, 4, 5, 6. Or you can be writing C's and H's and stuff. And then on one end I have to put a carboxylic acid. Just to be obnoxious, I'm going to put it on the left. That makes me draw backwards. But that makes my numbers go in increasing order. And then I number the parent chain, 1, 2, 3, 4, 5, and 6. And it's at this point on a test, if you did this, and then you ended up going to 7, you know to erase something. Right? And then I'm going to put a chloro group on the 4 carbon. So I'm going to draw a bond here, and then put a Cl. Okay? Again, you know, when you're doing this on a test, you have to draw structure, draw the parent chain, right? Put the functional group on it, number it, and then add the substituents. It's basically the same thing you do when you name it. Right? Okay, so reactions for carboxylic acids. Carboxylic acids can be prepared, this is actually a review from a previous chapter, can be prepared by oxidation of primary alcohols, okay, or oxidation of aldehydes. So there's 2 routes to forming carboxylic acids, but, well, there's more than that, but 2 that we've covered. You can either start with an alcohol or an aldehyde, and either one will get you to a carboxylic acid if you oxidize it. I checked on, remember I said I'm going to check the reagents? I don't remember if you remember me saying that or not, but for your final, to know whether or not you have to know like lots of different reagents. And the questions are basically, what do you get when you oxidize this? So if I say, what do you get when you get a mild oxidizing agent for an alcohol, what do you think that would give you, right? So here's an alcohol. I'm doing a mild oxidizing agent. It's really not that mild, but whatever. They don't actually give you the chemical. What do you think that means? What's that?
You need to know the reagent.
You don't need to know the reagents. And when it says mild, that means you don't take it all the way to carboxylic acid. Because the carboxylic acid is formed after you take a primary alcohol and you oxidize it twice, right? So if you just do a little bit of oxidation, right, you're going to end up with the alcohol getting oxidized to an aldehyde. And if you continue to oxidize it, then you'll go from an aldehyde to carboxylic acid, okay? And again, a couple of other things. We talked about oxidation is increasing bonds to oxygen, right? Just reviewing. So if we're going in this direction like this, I'm increasing the number of bonds to oxygen, so then that's part of the definition of oxidation for us. Yeah, if you let your wine sit out, or you have a leaky cork, right, and oxygen gets into your wine, oxygen can be used to oxidize ethyl alcohol, and then what it ends up doing over time is becomes an aldehyde. That actually has kind of this aldehyde has kind of a fruity smell to it. If I can, I'll pull some out in the lab and you can smell it. And then it turns sour, and that's when it becomes the carboxylic acid. And this is just acetic acid. This is vinegar. So when they make wine vinegar, they actually take wine, special wine, and they treat it with a yeast that helps to convert all the alcohol to carboxylic acid. Okay, and there's big business in that. They buy tens to hundreds of thousands of gallons of wine to just make vinegar. So, big market. All right, of course you could just leave your, I guess, open in your refrigerator too, I suppose. I'll let you read this, alpha hydroxy acids. It was just a little side note. But what does alpha hydroxy mean? It's alpha to the carboxylic acid. It's on the second carbon, right? So just when you read this note, it's more for people in the medical field that are interested in this. Okay, so let's talk a little bit about the properties of carboxylic acids. Like I said, they're used in a lot of foods. Monosodium glutamate is yeah, MSG, right? Yeah, sorry. Is used as a flavor enhancer. It gives you that sort of, what does they call it? The mame, the I don't know, it's one of those senses of taste that, umami, yeah? Umami, yeah. That's the umami thing. If you don't know what that is, look it up. It's kind of interesting. But yeah, you find them in a lot of different things that you eat. Okay, so carboxylic acids are really polar. How polar are they? Well, they have two polar groups on them, and they can hydrogen bond. Okay. So it can, if you think about it, if I drew another carboxylic acid on here, let me see if I can, I don't know if I can do this actually. I'll just play with it. If I drew it like this, you see how I just drew it, like turned it over and drew it, right? And remember, hydrogen bonding is a strong intermolecular force. It can hydrogen bond there, and it can hydrogen bond there. And that's one of the interesting features of carboxylic acids. And not only can it hydrogen bond to itself, but each molecule can hydrogen bond to another molecule twice. And in solution or in solids, a lot of times it forms what they call these carboxylic acid dimers. They actually just get stuck together like that. Okay, so let's see. What do you think that's going to do for their solubility in water? Huh? Remember, really hot, polar, right? Water's really polar, so it makes them more soluble in water. So again, up to about 5 carbons, carboxylic acids are soluble in water. Okay. What do you think it does for their boiling points? Really high boiling points, okay? So just a quick comparison, right? Here is a bunch of properties. I think we have most of it on the slide. So this is an aldehyde, right? So this guy here is an aldehyde. And then we're going through an alcohol and then to a carboxylic acid. So that's what we're going to be comparing, aldehyde, alcohol, carboxylic acid. Notice what happens to the boiling point. It goes from 49 all the way to 118, even though their molecular weight, they're about the same. So the high boiling point, right, even higher than an alcohol, has to do with these dimers that form. They like hydrogen bond with each other twice. That increases their boiling point. And that's what it says something about that up here somewhere. The other thing to notice, let's see. Oh, they don't have it on this slide. In terms of solubility, carboxylic acids are really soluble. I think that's on another slide. Yeah, higher boiling points, but soluble in water. And this is a better picture of the hydrogen bonding I tried to draw. Right. And I don't know, I thought these were pretty crystals, so I included it. They had it in the slide of the book. I'm like, oh, that's really pretty. And then I should have deleted it. It's just sort of gratuitous pictures. But this is a picture of carboxylic acid crystals, probably benzoic acid. But yeah, they can form hydrogen bonds between each other, these dimer bonds, to form really strong intermolecular forces. Okay, so what we're going to do real quick, we're going to apply some skills. We have 3 boiling points. We have to match them with compounds, and then we're going to say a little bit about why they have the boiling points that they have, okay? So I have 141, 110, and 36. Yeah, 141, propanoic acid. What's that?
100 is the 2-butanol.
Yeah, 100 is the alcohol. Oops, I drew that really sloppy and big. It's still sloppy, but that's okay. And then pentane, 36. Yeah?
It's the branch part.
What's that?
Bonds, the branching bonds.
Yeah, so let's talk about why it is, right? So that's 36 degrees Celsius for that one, 100 degrees Celsius, and 141 degrees Celsius. Okay, so first of all, 36, what kind of intermolecular forces does pentane have? Dispersion. It only has the one kind, the very weakest kind, has dispersion forces. Alcohols have dispersion, we'll ignore that for now because they all have it, has hydrogen bonding and is polar. So it has those two things going with it, all right? And then carboxylic acids, they're also hydrogen bonding and also polar, but they can form these dimers.
Can't see the difference.
Is it dimer or dimer?
No. Hang on. Let me fix what I just wrote.
Is it the ability
It's always from another one next to
for
it.
Just barely. Yeah, so by dimers, I literally mean, like normally when a molecule hydrogen bonds, I say, hey, I'm going to hydrogen bond with you with hydrogen bond one. Carboxylic acids are like fanatics. Like, I can hydrogen bond with you twice. I'm going to hydrogen bond with you twice. All right, and one, it goes like this guy here, like these guys here. The hydrogen bond forms both on this part of the functional group and on this part of the functional group. And that just makes the boiling points really high. Okay. So 1 to 5 carbons are very soluble in water, and then you go to decreasing solubility. It's pretty similar to alcohols, okay? Pretty similar to alcohols. Another property, oh yeah, so let me just leave it there for a second. So solubility up to about 5 carbons is normal. I start switching through slides really quick, and I realize some of you is just writing information down. So it's very similar to alcohols. And then as the chain gets longer and longer and longer, the solubility goes down. As the nonpolar part, all the C's and H's get bigger and bigger and bigger. Okay. Carboxylic acids, I talked about this a little bit. This is the reaction of carboxylic acid with water. This is the Bronsted-Lowry definition. And because it's, if you remember Bronsted-Lowry, carboxylic acids are Bronsted-Lowry acids with water. They're weak acids, and so let's go back and we'll review. Oh, that should be on my review slide. Weak acids. Weak acids. Okay, strong acids are things like HCl. See people trying to interpret my handwriting. Strong acids are things like HCl, HNO3. When you put them in water, what do? They completely dissociate. So the H and the Cl, for example, all of the H's and all the Cl's separate from each other. When we talk about weak acids, typically for something like acetic acid in the 1 molar range, it's typically only 1 to 5% that dissociates.
It'd be like a 6. Like a pH of 6.
Yeah, and so the pHs of carboxylic acids, like 10th molar range, are actually in the probably, what would it be? 1 molar is about pH of 2, which is about the same as your stomach. That's a lot of stuff, but more dilute, it's probably more like 3 or 4. Yeah, so they're a little more acidic, right? So what does a 1 to 5% mean? Only 1 to 5 molecules per 100 dissociate, whereas in a strong acid, it's 99% of them dissociate usually, if not more, okay? Like 100%. All right. Bronsted-Lowry acids. What's the definition of Bronsted-Lowry acid? Does anybody remember? It's something that Bronsted-Lowry acid is something that donates hydrogen atoms or ions. So let me review that. So this little asterisk here. Let me make a clean slide. I'm just going to abbreviate it Bronsted-Lowry acid is an H plus donor. So if you look at this reaction here, it's going to get rid of an H plus and donate it to the water here. And that means in the product side, right, water, instead of having 2 hydrogens, should have 3. So that's where we get the 3 from in the hydronium ion. And it has a positive charge because you didn't put a hydrogen over there, you put a hydrogen with a positive charge over there. So that's where that positive charge comes from. Okay, so this is the H plus donor part. And then water is the acceptor. And so that makes it the base in the Bronsted-Lowry definition. Okay. So the base picks up a hydrogen, the acid loses a hydrogen. Now, because it loses an H plus, that's what gives us a negative charge. That's where the negative charge is left over on the oxygen. Right? So it got rid of the hydrogen and a positive charge, so it had to keep the negative charge. What's the negative charge? What is negative charge always? It's electrons, right? It left its electrons behind, so that's what that means. That's where that comes from. Okay. So just some data to look at. It's a lot. I thought I would include it. If you look at boiling points, you notice the boiling points going up as the chain gets longer. Okay. These are all soluble up through pentanoic acid, then hexanoic acid becomes slightly soluble Benzoic acid is very slightly soluble. The acid dissociation constants. Remember, we talk about Kas and pKas. All you have to know is that they're weak. Their values are 10 to the minus 4, roughly. You notice they're all roughly the same, 1.8 times 10 to the minus 4, 1.8 times 10 to the minus 5, 10 to the minus 5, 10 to the minus 5, 10 to the minus 5. So basically, they're all the same in terms of their acid strength. Other than methanoic acid, which is a little bit stronger, they're all about the same. Okay? And dilute solutions will produce slightly acidic pHs. Okay. Yeah.
Are we going to be using the constants, right?
No. In fact, I'm not sure why they put constants here when usually they just talk about pKas. If you look at the pKas, they're all 475 roughly, 4.7. Really what I needed was water, but then I had coffee. It's just like water with extra stuff in it, right? Okay, so we're going to write the balanced equation for the ionization of butanoic acid in water. And the ion that's formed is known as a carboxylate ion. So we're going to go ahead and write this out. So I have butanoic acid with water. So what I'm going to do is I'm going to be lazy. I'm just going to write plus water. And then I'm going to write everything else below it so I have plenty of room. So it's an acid, right? So it's the acceptor or donor? It's the donor, so it's going to lose a hydrogen. So you write the same formula over. In fact, if it helps you, just write the exact same thing over and then scribble it out. So that's the exact same thing, right? But it was the donor, so then you take your eraser out and you scribble off the H and then leave a negative charge behind. Okay. The other part? H3O, because it's going to be water is the base, so I get H3O plus, like that. Okay.
Why is it the donor?
Just because that's the definition of an acid. Yeah, hydrogen donor is the acid. So if I say, what is the balanced equation for the ionization of butanoic acid with water, then I just have to know that the acid is going to give up the hydrogen and the water is going to receive it. Okay? And then just keep track of the charges. Okay. Like anything else, it's something you could memorize too. Okay. What else do I want to say? Just the. Oh.
That product, is it still butanoic acid?
No. So the name of this ion. Okay. Do you guys remember the white mouse ate icky cheese?
No.
What? Good Lord. Raised in a barn. Actually, my mom was raised in a barn for a while. Or no, actually, she was in the tent next to the barn. You know when you, yeah, anyways, long story. I'll tell you guys sometime. It's just crazy, crazy stories, family stories. Not that you need to know them. It's just a kind of interesting part of American history, CH3. Sorry. Let me do it here. I'm going to do it with one example. So this is ethanoic acid. And there's this saying, the white mouse, that's an H, not the right mouse. Ate icky cheese. So if the acid ends in ic, it's anion, it's conjugate base. Remember Bronsted-Lowry definition has this thing called conjugate base. Then the conjugate base ends in 8. So ethanoic acid, when it does this reaction with water, forms this ion. And so ic becomes 8, so this becomes ethanoate. Okay? That was the naming trick for acid, anion names to acid names. And 8 goes to ic and ite goes to us. And that's this part. Could make a rap out of that. The ite goes to OUS, right? Yeah. Somebody make a rap out of that. Well, never mind. We could make a music video. We could like.
Extra credit.
No, it's just fun. The extra credit to have fun. I know you guys are students and you don't have much time for fun.
There probably isn't already.
I know. I know, but it's more fun when you do it yourself and make a fool out of yourself.
No.
Okay, we'll make a fool out of you then. So what is it? Sorry, I don't mean that. What is this one going to be called then? Butanoate. Yeah. But I have like another half hour I get to go. I forget how long you get the lecture in here.
2 minutes.
Robbery. Yeah, so there's a slide on it. Methanoic acid, methanoate. So usually if it's like a neutralization reaction, you get the sodium with it, like I showed in the very beginning. This would be known as sodium methanoate or sodium formate, or potassium benzoate or sodium benzoate, and that's the preservative you see in food all the time. That's the one that if you mix it with citric acid and heat it, produces benzene. If you know anything about benzene, it's really not good for you. So, just saying. All right, good. Is there a ban on it? Not as far as I